Okay, so welcome everyone. I am Manu Upadhyay. I am assistant professor at the École Polytechnique, and I'm also in charge of organizing the seminars for LMS. Today, it is my pleasure to invite Thomas Pardoen, who is a professor at UC Louvain in the École Polytechnique of Louvain. To give you a background about Professor Pardoen, he received his engineering degree and master's degree in philosophy and PhD in applied sciences in 1998 at UC Louvain, back when the École Polytechnique was called Faculté de Sciences Appliquées. Then he did a postdoc at Harvard University and came back to UC Louvain in 2000 as an academic. He is now a full professor at the École Polytechnique of Louvain, and he has received a Grand Prix Alcan from the French Academy of Sciences in 2011. Since 2014, he is the president of the Scientific Council of Belgian Nuclear Energy Study Center, SCKCEN. Since 2015, he is the president of the Institute of Mechanics, Materials and Civil Engineering of UC Louvain, and he was awarded the Shear from the University of Liège in 2015 as well, and a fellowship from Euromech. He is currently the board member of the Journal of Mechanics and Physics of Solids, Engineering Fracture Mechanics, and International Journal of Damage Mechanics. His area of research is very wide. He has worked on a lot of different topics, and today he's going to talk to us about the micromechanics of deformation and fracture in highly cross-linked thermosets, impact on composite modeling. So thank you, Thomas, and please, the floor is yours.
Okay, thank you, Manas, and thank you to all of you to be there today. I would say usually it's good to see you. I think it's better to say it's good to feel your presence behind screen. From a purely egoistic viewpoint, of course, I would have loved being in Paris, spending time with the colleagues, coffee and a good dinner, and have all these social contacts. Of course, we are lucky people as scientists. At the end of the month, we still have our salary. We can do what we like. We can continue working on our research with some difficulties for the experiments, but we have time to read. And so compared to other people, our life is probably easier. Also, science right now is considered in many countries, unfortunately not all countries, but in many countries, science is recognized as important. Scientists are listened. I don't know. Well, we see a little bit what is happening in France from Belgium, of course. In Belgium, we see the colleagues every day on television, and the politicians respect what they say. So this is positive certainly for science. But on the other end, science is also teamwork, is also a social activity. And weeks after weeks, I can feel that we're missing more and more these connections, or where it gets more abstract, and so I have a mixed feeling. And of course, I'm very happy to be with you today to talk a little bit about a subject which is an important subject for a group now for, I would say, a little bit less than 10 years. We started with composite research, polymer-based composite research, more extensively something like 12 years ago. And of course, the field was a field already very advanced. And we realized that the contribution, if we could find an interesting scientific contribution, would be to bring our knowledge more from the field of metal science and into this world, and focus on the response of the matrix on the thermoset material, and try to understand better the deformation mechanism and the fracture mechanism by borrowing, of course, elements from other fields, and of course get to know better what is going on inside polymers. And for this, I have had the chance to work a lot over the years with my colleague Christian Bailly, who is a polymer specialist. You see other names in the co-author. Everything I will be showing, of course, come from the work of excellent young and less young scientist, Xavier Morel. You may have heard about Xavier. He's on postdoc right now in France. Jérémy Cholavalier was a PhD student. He's now working for Solvay company together with Frédéric Lany, who is also in Solvay, who was a former senior scientist in our group. Frédéric Van Loock is currently a postdoc working in our group, and the video you see is coming from Frédéric. Laurence Brassard, many of you know Laurence. She's now professor in Oxford, and for many years now we're interacting quite a lot with Pedro Camanho from Porto on the subject. So what I would like to discuss with you today are some, I will start with a few basic questions to set the context of what we are doing. And I'm not saying we had these questions at the beginning and that then we had a strategy to solve this question. It's more that over the years we found several interrogations, and now I'm using that to motivate the presentation. The first one is here on this slide. So you see on the left side the response through stress, through strain, compression tests that are performed on UD composites. The experiments are the blue lines, and the finite element prediction are the triangles there. So in order to produce this simulation, what we did was we tried to use, and I will come to that during the talk, the best possible continuum mechanics model for the matrix. Very careful, and that's what you see on the right, very careful identification of the constitutive model using compression, tension, torsion models at different rates, etc. And the fitting was excellent, so good. Fibers, we know what to put. It's a UD on the compression. It's an easy problem. And this is the best we can get. So our predictions are 15 to 20% below the experimental data. And we have not put any damage. Huh? If we would put damage, things would be worse. The curve would be even lower. And we do see damage experimentally. So, and we tried many things, and honestly, the only conclusion we can get is that the behavior we put for the matrix is not correctly describing what's going on. And there are two options. Option number one, the material itself is not the same as in bulk form. So the way the cross-linking process, the curing, is occurring at a length scale of a few micrometers due to different heating condition, heat conduction with the fibers, the volume confinement, etc., modifies the structure of the polymer compared to bulk form. That's option number one. So we think we do model the right polymer, but it's not exactly the same. The other option is that a continuum model with a classical form is not rich enough to capture the plastic behavior. And indeed, we're talking about elastoplastic behavior here, that it's not rich enough to capture the detailed flow field at that length scale when you are in volumes, again, on the order of a few micrometer size. Similar to what we have in metals, by the way, where people develop strain gradient plasticity theory, etc. So two possibilities, and that's one motivation for today. The second motivation, and for those of you working in the field of modeling polymers, you have seen many papers over the years, starting with the work of Mary Boyce, Eric van der Giessen, Lalita Nand, etc., doing excellent works, relying on empirical phenomenological models, but also rooted in some micromechanical analysis and the argon idea, etc. And over the years, the models have been improved, enhanced, and they're doing a very good job. If you read the more recent one, they can predict a lot of stress states at different temperature, even sometimes below and above TG, but at the expense of a very large number of parameters, at least 25 or more. And so, and this has to do with the complexity of the response of typical thermoplastics and thermosets. Even though I will talk about thermosets, most of the things I will discuss today are valid for thermoplastics. So as you know, a polymer starts with a linear elastic response and non-linear elastic, then plasticity starting, and we never know exactly where. It's not easy to decide where there is true plasticity, and even the notion of true plasticity is not totally appropriate in polymers. We have to define plasticity with respect to a certain time scale. Then you have this softening response, and then the rehardening due to the alignment of the polymer chains. And when you unload during a test, you see huge nonlinearities, very significant Bochinger effect, more than what we see in metals. And then if you stay at zero stress, you get partial recovery. And on top of that, huge rate effect, temperature effects, pressure effect, deformation-induced anisotropy. So it's not a surprise that we need many parameters in phenomenological models. But can we perhaps do better? And of course, there will be a cost for that, with more physics, meaning capturing these effects with a lower number of parameters. And the additional question, the side question is, of course, is it important for composite science? So in my title you have the impact of this on composites, but I will not say too much on composites because it's too much, and honestly, we have not yet been able to apply all the things I will present extensively to composites. But the question maybe, is it important to take into account all this when working on composites, where we know the typical strains we apply is rather limited? And we can discuss that at the end if you want. Sometimes it is important, but not always, but sometimes it is. A third motivation for this work, and I'm already showing you a nice fractalography, is the better understanding of the physical mechanism of fracture in the thermosets. So people are looking at that for a long time, but we don't see, at least perhaps we missed some part of the literature, but we don't see evidences of advanced micromechanical studies of the phenomena of fracture in thermosets compared to the level of understanding in metal. So really fine, low-scale understanding of what caused initiation of fracture and what are the detailed mechanism. And I want to say a few words today about that. So this is the outline of what I would like to discuss over the next now 30-35 minutes, and Manas will interrupt me when he thinks that he sees too many people leaving the room, because that's the thing, with the video, it's easier to escape. So to escape from.
No worries, I will let you know.
Right. When the number decreases by more than 10%, you stop me. Good. So this is the outline of the subject I would like to cover with you. Very quick. 2 slides on the material on which we have done quite a lot of work over the last something like 8 years, I would say, or even more, the so-called RTM6 materials. Then the blue box is 2 chapters on the deformation part and 2 chapters on the fracture. And it's always the same, some test results, and then the models that we have developed recently to try to learn from these experiments and to bring some new approaches in this area. Okay, so I will not spend too much time on the chemistry of the RTM6 process, of the RTM6 resins. RTM means resin transfer molding, so it's one of the recently preferred method to produce high quality composite parts, used a lot in aeronautic industry. And this specific resin Is not anymore the best one. There are better one, but it's a typical resin for carbon fiber reinforced polymers that I use quite a lot in aeronautic applications. There are better resins today with higher performances, higher fracture toughness, but still. It's a tetra-functional epoxy, meaning that there are 4 functions here that can link to a highly reticulated material. The TG is above 200 degrees C, which is important. It means that at room temperature will be very far from TG, meaning limited viscoelasticity. In order to apply mechanical models and do micromechanics on the RTM6, of course, we need to produce clean samples. And it's not that easy to produce bulk specimens that are very clean, without porosity, full curing, no burning, etc., etc. So it took some time, especially to Xavier Morel, to be able to produce big slabs of materials from which we can extract decent size fracture mechanics samples, this notch test sample, tensile bar, compression, traction, torsion, shear, Josipescu type specimens. So yeah, that was quite a work to define the best curing schedule for that. By the way, many of the tests I will show today are coming from compression. And I will show a few results on composite, compression of UD composite as well. Compression is nice, of course, because this material is not very ductile. And if you want to address the large deformation behavior, you can only reach it in compression. Let me start with giving you some an outline of the main characteristic of the deformation and strength of these materials. On the left, you see the schematic stress strain curve, and on the right, some specific data. I'm starting with the elastic response, and what you see here is Young's modulus as a function of strain rate, almost no effect. And like I said here below, it's more important regarding viscoelasticity, storage modulus, loss modulus, which is very small. And so viscoelastic effect of strain rate, for instance, on the Young's modulus will be quite limited for what I will discuss next. But on the other end, the viscoplastic behavior is significant in terms of the rate sensitivity. So on the right side, you see blue, red, and green curves, 3 different temperatures, so big effect of temperature, of course, and big effect of strain rate. The curves are given for 4 different strain rates, displacement rate here, so these are displacement rates, where you see big effect. This is below the evolution of heel stress with strain rate. So by the way, at room temperature, for the metal people in the audience, it's good to realize that the heel stress of these materials are above 100 megapascals. So compared to a typical aluminium alloy, not the best one, we're not far. So heel stress is large. Of course, the Young's modulus is close to 3 gigapascal, which is way lower. But the heel strength is really decent when compared to many metals. This is more entering now more specific questions that we addressed. Upon unloading, you see here compression tests that have been unloaded, and we monitor the unloading as well as the recovery. You see the recovery below when the stress is 0. And this is the curve showing you the strain that is recovered when the stress gets down to 0 as a function of the strain that was applied before. So if you apply 60% strain and then you unload, you recover, so typically 2–3%. After you have, of course, recovered another part of the deformation, so you're getting almost to 0. Now, if you deform by 60%, you unload 50%, you unload 40%. Sorry, it's true strain, so I should not say percent, but it's easier to discuss. So 58, you unload, you get 40%, so 18% during unloading with a huge nonlinearity, and then you're recovering another 6%. And then you can wait for years, you maintain the strain. So this is plasticity. Yeah? It's not that with more days, you will recover it entirely. Yeah? So the plastic strain stays, this is plasticity. If you eat the material near TG, then you're recovering the strain. Not entirely, but almost entirely. So definition of plasticity is always, might be controversial. Something more sophisticated. You load the material up to about 10%. And there you maintain the force. So you do a creep test. Of course, the material creeps, the true stress decreases because the material keeps deforming, and it's a compression test. Your section is increasing, so the stress is decreasing. So you do a creep, then you unload, and you see the unloading. Now we're gonna let it creep longer, and again unload, and look at the unloading curve. Immediately what you see is that the amount of nonlinearity upon unloading is much lower when you let it creep long. So it's like if by letting the material relax by creep, you do something, and we will explain that later, you let the material stabilize in such a way that during unloading you have less Bochinger effect, if you want, which will be related later to backstress. Another very interesting experiment, and by the way, we thought that was a really recent thing. We found only a few papers showing this experiment, and then someone came with an old paper. I don't remember, it's from the 60s or 70s showing this. So this is not new, and of course, a lot of good things have been done in the past. It's also called the Colroche effect, what I will explain here. So let's do a compression test, maintain the force and let it creep. That's just what I discussed before. It's the blue curve. And, or you just unload and you go to zero stress and you have recovery. There is the interesting question to find the stagnation point. So there should be a stress at an intermediate value where you don't creep and or you get recovery. So let's try to find this intermediate level of stress where you will be just at the intermediate level. So let's reduce the stress. So you do your compression test, you load by 20%, you maintain the stress. What happens? You get creep, forward creep. It's a compression test. So basically the material keeps compressing under that constant force. And if you go down to 60%, what you have is interesting. You start with a little bit of backward creep, so a little bit of recovery, followed by forward creep. So you're not finding a stagnation point. You find a condition where the material keeps recovering a little bit, so meaning under, so it's compression. So you have a compressive stress, you maintain the force, and the material elongates a little bit. And then if you wait longer, it keeps deforming by positive creep. Okay? If you do that at 50% force, 50% load, you get a lot more recovery, but at the end you're still having a little bit of creep. And then if you are 25% on load, you only see that if you maintain the stress at that level, even though you are under stress, the material elongates. It's a compression test. And then the material elongates. And at zero stress, we said you get recovery. So it's a very interesting phenomenon. And basically with the I think all phenomenological constitutive models that are available, this you will not be able to predict. By the way, this is something that has been observed on nanocrystalline metals, and the origin is related to very significant back stresses. So you got the message here about this creep recovery and this stagnation, non-stagnation point in this rate reversal effect that we found here. Now, typical results known for a very long time on polymers, of course, is the effect of the stress state that is applied on the plasticity. So you get a compression curve here, a torsion, and a tensile test. Unfortunately, the tensile test breaks before getting full plasticity, but you clearly see that there is an effect of pressure dependency, which is well known. And then we perform other kind of activation volume measurements, and I will explain later what is activation volume. I think many of you know that. You have here on the left, we perform strain rate jumps. So where during a compression test, we suddenly increase the rate, then continue the test, then decrease the rate, continue the test, re-increase the rate, so jump of strain rate. From that, you can take the derivative of the stress with respect to the derivative of the strain rate. And based on that, you can extract the rate sensitivity exponent, but also a parameter named the activation volume. And the exact definition is given here. And it is an imprint of the fundamental mechanism taking place at the nanoscale and giving rise to the plasticity mechanism. And I will come back to that later. Typical value that is obtained is 0.5 nanometer cube. And there are other ways to measure this quantity through relaxation tests, through recovery tests. You have to make some assumption, but I will skip that for the sake of time. But at the end of the day, when we combine the jump test, relaxation test, recovery test, and we perform that at different true total strain, the activation volume we measure changes a little bit with the strain, but not very significantly, and is always about 0.5 nanometer cube, which means that there is a phenomenon taking place at that length scale triggering the permanent deformation of the material. And a final experimental result I would like to show is the following. These are now tests on composites with aligned fibers. It's a compression test on a UD composite. And the reason I'm showing it is not to look at this nice fracture event. This is not my purpose. The purpose is that we very distinctly see a shear bending process. You see, and there are many examples of nice shear bends that are observed and which later on developed into a damage localization. But at the beginning, it's a very distinct shear bending process. And we see it very well in this composite configuration. Typical thickness is way below 100 nanometers, but we cannot measure accurately. But there is definitely a shear bending process. In order to, okay, so let's go to modeling now. The first thing we did was, with Xavier Morel in his thesis, was to look at available empirical models, phenomenological models, and in order to use this model for composites. So then to make the simulation I mentioned at the beginning, simulate a UD composite with a nice constitutive model for the matrix, then the fibers, turn the crank, and get good predictions. And you know the story, we're not getting very good predictions. So decided to take a model with an intermediate level of complexity, to use Abacus. We use Drucker-Prager with a rate-dependent hardening law. I'm skipping the details. 28 parameters. This is typical cost for these types of models, where and based on these 28 parameters, you can predict all different temperature, different rates, tension, compression, torsion, and a few more things. These are the 28 parameters. But we are not able to capture the complicated effect during unloading. We would probably need 10 more parameters for that. So that was the time. And at that time, we also started working on metallic glasses, completely different subject. And we looked at the literature there, and we read these papers by the group of Chris Shu on metallic glasses, where they use the so-called STZ model, shear transformation zone based model, and in order to represent the behavior of metallic glasses, and showing very good trade-off between, we thought, complexity and accuracy, or capacity to predict the different phenomena they were observing in metallic glasses. And we had then the idea to say, but well, probably in our thermosets, based on what we have read from MD simulations also, we could probably use the same formalism. And basically this formalism comes from Argonne idea, who unfortunately passed away a few months ago. And in the mind of Ali Argonne, the idea is that this STZ approach is generic. It's generic to even for dislocations or for polymers or metallic glass. So we decided to look at the work of Chris Shu and then apply it and see what we should do to convert it, to modify it, to apply it to polymers. The idea is the following. This is the schematic here. The idea is that the amorphous material is made of an heterogeneous medium with zones that are particularly fertile for undergoing a so-called shear transformation, which means at the scale of molecular chains, a so-called crankshaft mechanism or a rotation of a side group or something like that, which is a permanent mechanism. Permanent in the sense that if you need to apply an opposite force significant enough to overcome back the barrier that you had to overcome to go from one equilibrium state to another one. This phenomenon induces locally a shear at the atomistic scale. And so basically the plasticity of an amorphous material of that kind is just the accumulation of the activation, a lot of this transformation. And of course, when one element transforms, when one region transforms, the neighboring element, even though it may not be in a fertile region, is undergoing a large stress concentration, and its transformation will be favored. So there will be interaction effects. The idea of Shu and his group was to use finite element method to solve the elasticity problem. So basically, it's an elastic problem interacting with a U-mat that takes care of the triggering and activation of the STZ. In order to do that, you create a finite element mesh. You decide what will be the size of your possible STZ. You provide to every element a certain energy barrier and some parameters I will describe next. And then at every increment of the calculation, you go over all elements and you check whether or not one element or one group of elements should be transformed because it has attained the criteria for triggering an STZ. And the finite element formulation takes into account the redistribution of stress using an elastic framework. A few words about the formalism. The rate of activation of a shear transformation zone is given by this expression, and the derivation of it you can just follow transition state theory. The rate of activation depends on the energy barrier, and which is reduced by the mechanical driving force you're bringing if you impose a shear, and this shear will work through the transformation strain over a volume, which is the activation volume, which I defined earlier. Now, there is a little bit of subtlety. What we found experimentally is not gamma zero. If you take the derivatives, etc., what you find experimentally is the strain multiplied by the true activation volume. But you got the idea. And so there is a certain activation rate, and which of course will depend on temperature, and higher is the temperature, higher is the probability that you can do the jump over the barrier, and also this probability increases if your mechanical driving force increases, meaning if the stress is larger. The probability of activation is the activation rate multiplied by the time increment over which you're looking. And we use a kinetic Monte Carlo algorithm where you generate a random number between 0 and 1, and if this number, if the probability is lower than your random number, the STZ is activated. The question is, what is the form of the energy barrier? The energy barrier, we just borrow what Argonne has proposed, and that's what Shu is also doing. Basically, for an STZ to transform, it has to accommodate, you have to accommodate shear and dilatation. And using SLB theory, you can approximately predict what will be the shear energy that will be associated to the shear transformation and the dilatation. This is an approximate solution, but it's nice because you know in advance what is the value. And it means that in your formalism, you don't have to attempt a transformation and then go back if you have not overcome the barrier, which would make the numerical analysis more complicated. You also have the cohesive term with respect to the intermolecular resistance that you have to overcome to make this transformation. There is an effect of the free volume that is present in the material, taking into account the dilatation strain during a transformation. There is a dilatation strain, and it is known that there is production of free volume. And we added a term which is related to the fact that when the chain will align, we will need an additional resistance energy contribution to the energy barrier, which is typical to polymers. I will skip the story about the activation volume, the free volume, and as a matter of fact, we put it at the beginning to follow the work of Shu, but the recent analysis we've been doing, and Frederick Van Loock is looking at that, the recent analysis shows that it's a secondary effect for most of the predictions. So I propose to skip this. If you want to read more, you can read in the paper. And we proposed a very phenomenological approach to take into account the effect of the hardening coming from the chain alignment, introducing related to the stretches, and introducing an extra parameter here, which has an energy form. So by the way, there are 9 parameters: a shear transformation strain, an activation volume that we can measure experimentally, Young's modulus we can measure, Poisson ratio we can measure, intermolecular resistance, it has a physical meaning, but basically you will need to adjust this value. A fitting parameter taking into account pressure effect, a fitting parameter connected to the dilatation occurring during a transformation, a fitting parameter related to the annihilation of free volume, but that's not very important, and a parameter to adjust for the chain alignment. So 9 parameters, 3 or 4 of them can be obtained directly from direct measurements. Okay, so these are some simulation when you just turn the crank, and it seems easy, but there are some subtleties, and Frederick, for the time being, is really spending time on trying to regularize some effect of time stepping, etc. So I think now we have a fairly reliable code and fairly reliable version that converge if we decrease time step, etc., etc. You see nicely, and the little dots you see, this is maximum principal strain plotted here, by the way, and you see the transformation starts, few STZ, then they trigger some patterns which directly you see are organized under maximum shear. Now, the goal was to go beyond developing the model. This was to, and get qualitative result. We really wanted to push the game to really identify the parameters and make direct comparison to our macroscopic experiments. So in order to do that, these are the stress strain curve. Here, the experiments are in red, and the model prediction are the dotted lines. When you see me looking like this, it's because I have my camera in the middle of the screen. All right, so we have been using the test at room temperature to adjust the 4 fitting parameters which are here. The pressure dependency, we need one more test. These are compression tests, by the way. We need a tensile test or a shear test to adjust the beta parameters. But we use one curve to capture the rehardening, the softening, and the right plateau value here. So in order to adjust these 4 parameters. And the 2 curves below, these are different tests done for different parameters, just to show that we did the parametric study. And these are the predictions that you get for the 2 other temperature by keeping the parameter constant. So the model does a good job. Just look on the left. The problem is that the model predicts a much larger overshoot peak stress here. And I will come back to that. And we know where it is coming from, and it will come back. So this is just a larger picture where you see the predictions. Okay, you may say that that's okay. It's the minimum we expect from a viscoplastic model for polymers, it's to capture the temperature. These are some more snapshots taken at different deformation steps. This is intention, just to show you that at B here, we start having the first activations below the peak, and the peak stress is when we start percolating some pattern of shear bands, a collective behavior of some STZ, now creating plasticity which go at the macro scale. And during the softening, that's when we have now this pattern developing into the entire specimen, and the rehardening starts after 40%. Okay. This is the compression test. It's exactly the same idea. I will skip this one. Very important messages here. And it's confirmed by MD simulations. I mean, qualitatively, we compared, we looked at some papers in the literature, and MD shows this kind of thing. Sigma 2,2 is the value of the stress at every single point. So this the value of sigma 2,2 recorded at different points in the mesh, and sigma 2,2 bar is the average value of sigma 2,2. You have 4 colors. That's for the distribution of stress sigma 2,2 normalized by the applied stress. It's a compressive test again. And this is the distribution at 2% compression. But the stress level is everywhere near the applied stress, no surprise. At 5%, you get some distribution, meaning that in some regions you get transformation, in other regions you don't, and there is a pattern of stress. But look at 30% or 60%. The distribution of stress is enormous. Up to a point where some of the stress, some elements of gauge point level, they show stress which are opposite to the applied stress, meaning you're under compression, there are regions of the material undergoing tension. So the distribution of internal stress, or the distribution of stress, is huge. And this related to this heterogeneous process of transformation. Yeah, before I'm using what I said, I just want to mention this. This is a compression simulation where you go to from the peak stress, you have the softening, and then the rehardening. If you unload after 20% or 50% and you reload, oops, sorry, you see that the peak stress is now much smaller. Basically, you have what is called in polymer science rejuvenation, meaning that after a deformation step, you have activated, you have put excess energy into the material, and you have reduced the stress that you need to put to continue the plastic deformation. And basically, when we start with a mesh with no excess energy, basically we always overestimate the peak stress. But the reality of the polymer material is that it has not undergone necessarily a long aging. It is in a state between aging and rejuvenation. And to make something that is realistic, you should prepare, like what you do in MD, you should stabilize, or here you should do something which represents the history of the material, and basically you have to deform it a little bit to create a landscape such that when you start your test, you get the right peak stress. By the way, if you unload and reload in a different direction, you see a difference. It's not big. It's not as big as what we see experimentally, but you see an anisotropy effect that is predicted with the model. The most important is this, and this was really the thing we were very happy. You remember the experiments here that I explained where you have this forward creep under full stress, recovery, and this stagnation point here where you have backward and then forward creep. Guess what? The model, without any new tuning, is capturing this in a certain range. If you perform a creep test at something like 25–30% of the load, you're getting first backward creep, sort of recovery, followed by forward creep. And of course, it's not right to the point. Experimentally, we see this at 60% and not at 25%, whatever. The message is that the model is rich enough to capture a mechanism like that without, and there are many, many, many improvements you can do, of course. And this has to do with this landscape of stress, heterogeneous stress development. Just the fact that when you unload, even under loading, you're already getting regions that are undergoing tension. So as soon as you're unloading, these regions are getting more and more in tension. They get to a point where they reach the peak stress in tension, and they start activating plasticity in the reverse direction. And of course, when this mechanism has been exhausted, then your stress is still positive. So you get the forward loading. This is explained in more detail on this slide, but I will skip it. But this is the idea. So it has all to do with back stress effect. There is nothing else to explain this phenomenon. It is all related to the stress heterogeneities that are created. This
so now,
just yes.
We have 5 more minutes. Is that okay?
Yes.
Yeah.
Sure.
Thanks.
Sure. I'm done with this part, and I will just say a few words about fracture, just to give people the envy to have a look at the papers. But
Sure.
No, I will respect the time. Don't worry.
Thanks.
And you know what? I told you, my grandmother is turning 100 years old today. So just after the seminar, I'm gonna go to say hi. So I've also reason not to extend it too long.
Yes. Great.
So with the beta parameter, you can introduce pressure effect, but that's not a big deal. No question now. Are we solving our problem from the beginning that with this more physical model, we can capture better the response of a UD composite? We have mixed answer at this stage. This is ongoing work. We certainly capture the plasticity pattern when we simulate a part of the UD with the STZ model, and you compare with experiments, you see a fine pattern here that is in very good agreement visually with the experimental data, and as well with recent DIC measurements that I forgot to put. This is the pattern you're getting with the Drucker-Prager model. So it's not so bad, but you don't get these several patterns, several shear bands pattern that we capture here. This is the positive message. The negative message is that we are not seeing much of strengthening coming from this model when it's confined in small volumes. And as a matter of fact, we don't get, like in these locations, far field long range effect, which accumulate, which can create the strengthening. So there's still something to understand there. And I'm not saying that with this STZ model, we're solving all the problems by far. A few minutes to show you some pictures about fracture, and I just want to give you perhaps some experimental motivation, and regarding the models, I will just let you read, if you are interested, the papers. But we perform tests on notch specimens, shear specimens, compression specimens on RTM6. This is the fracture strain, the true equivalent fracture strain under different stress triaxiality from compression, shear, and I forgot to put the point with shear, but there should be another point for shear here, uniaxial tension, different notches, and different temperature. And you see a clear effect of stress triaxiality. So if you want to develop a micromechanical model, it should be able to capture a trend like this. We measure carefully the fracture toughness, and it's known in the polymer field, you have to be very careful in the way you introduce the pre-crack. And if you just use razor blade sliding and not taping, you measure a fracture toughness that is twice on average the value of the real one, so very careful. And we perform fatigue tests, and the main message here is that if you do a tensile test after a long fatigue, you don't see much difference in the response. So the fatigue is not leading to a lot of reduction of stiffness or strength. It's only at the very end, you're generating defects and the material breaks. So it's not the incubation time is very long. I will finish by showing you some nice micrograph, fracturography. This is RTM6 broken, and this is when you zoom in this initiation zone. And it's fairly interesting to see that you have a sort of defect. The defect is here, the defect is here, the defect is here. By the way, this is for fatigue and uniaxial tension, and we see very similar pattern in fatigue and uniaxial tension. Then around the defect, you have a flat region, a mirror-like region, and then you have a small, I don't know if you see it, but there is a very small narrow ribs of 2-3 microns here. And then you get the failure brittle pattern with the river lines. If we zoom in along this flat plateau, and I'm looking below here, you see this plastic zone. We think it's a plastic zone, and we have reason to believe. It has the size it should have for a plastic zone based on the fracture toughness. You see this zone. If you put a pre-crack, a very sharp pre-crack, we don't see the flat zone. Basically, we only see the plastic zone. It's like if the pre-crack is sharp enough to play the role of this flat zone. So the message we got from analysis of the fracture surfaces is the following. For a specimen without a pre-crack, let's say start with a pre-crack here on the right. If you start with a pre-crack, you load the specimen, you get blunting, a little bit of blunting, you get a plastic zone of about a few micrometers in agreement with what you expect, and then the crack propagates. If you start with a smooth specimen or a notch specimen, anything with no real pre-crack, there are always some tiny defects in the material. There is a nucleation process, something around the defect. There is this fast crack, which stops. There is a crack arrest. And then there is a reloading phase, a little bit of plasticity, and then crack propagation. This is what we observe, and now we have looked at other thermosets, and we do see the same. We don't understand why the crack arrest exactly. What is the condition for the crack arrest and the reloading? All the numbers, all what you see makes sense when we compare them, but it's still a bit unclear for us what exactly sets the size of this first nucleation, then the stop, etc. So, but we found that interesting. The last 4-5 slides that I will skip show you the model that we have developed, and there is a simple model to predict this effect just based on 2 parameters. an aspect ratio of defect and a critical stress of about 300 megapascals, which can be used to rationalize the notch test, tensile test, the compression test, also to predict the compression, as well as the fracture toughness specimen. All right, I'm going to go to the conclusion, not to be too late. I've been a little late, not long, and we had this bad stop in the middle. This is the conclusion for the viscoplastic behavior. You have seen that the behavior of thermosets depends a lot on the heterogeneous nature of the deformation, even more than on metals, for those of you who are more from metallic field. The STZ model that I've explained is very efficient. With 5 + 4 parameters, we can capture a lot of things. Of course, we cannot use it for a structural simulation. I've not said this, but the size of the STZ is nanometers. So we can simulate regions of micrometers, not millimeters. So basically, you should see this model as interesting for science, for looking at small scale effects, and you can use it to fine-tune continuum models that will still dominate if we want to model more structural engineering or bigger problems. And I have explained you a few things about the failure process, and this is not typical only of RTM6, but recently we looked at other thermosets and we found the same scenario. We propose a micromechanical model for that, but still there are several unknowns, very interesting to understand. And I would be happy to know if some of you have more ideas about it. And I thank you, all of you, for your attention.
Thank you, Thomas. The floor is open for questions. Please either type it in the Zoom chat as QUESTION, or I have a question.
Manas, I have a question. I raised my hand.
Ah, I didn't see that. Go ahead, Julie, please.
Okay.
Yeah.
Hi, I'm Julie Diani, and thank you very much for your presentation. I'm interested in the constitutive equation for the thermoset in the glassy state. It's a very difficult topic. A lot of papers have been written on proposing some constitutive equations, and so I have two questions. I'm going to give you my questions and both, and then you can answer. First, I don't really understand the concept of non-viscoelastic material, elastoplastic material with some kind of residual strain when you unload. And second, there are some models now that have been developed, for example, by Professor Nguyen in Johns Hopkins University, and some other have followed the same path, using all we know in terms of the fact that for thermoset, linear viscoelasticity extend to large deformation. And I would like to know, we can discuss this. And
yeah.
Okay.
Yes. So you understood, I'm initially not from the polymer world. Of course, well, I did some work during my postdoc more than 20 years ago, but then my main field was metal. So I think it's a very interesting subject and with no good answers. And for a long time, when I was talking with my colleague, Christian Bailly, he said, yeah, Thomas, what you call viscoplasticity is just nonlinear viscoelasticity. Let's agree, we have different terminologies, etc. And so at the end of the day, I'm not really sure anymore what to do, because so if you look at these graphs here, and so you load by 50%, you unload, and you wait for 1 year, you still have a permanent strain. And in the vocabulary of plasticity, this is called plastic strain. And I think 100 years later, you will still maintain some strain. So
the fact that you recover due to higher temperature proves that it's just
exactly.
a matter of relaxation times.
Yes, exactly. So at the end of the day, I think it's just a matter of vocabulary. If you want to correlate nonlinear viscoelasticity with enormous relaxation time, for me, it doesn't change much, especially now we're working with this STZ model, not anymore invoking yield stress function, etc. So basically, I think it's worrying me a little more when we start talking about yield surface and then mixed with viscoelasticity. Then this is theoretically more complicated. But I agree with you. If now we only look at the physical mechanism at molecular scale, alpha, beta transition, and then the gamma transition, and for us, we put that into the STZ formalism. I don't need to call that nonlinear viscoelasticity or viscoplasticity. So it's more a question of, I think, of terminology. I'm using the word viscoplasticity. I'm saying there is not much viscoelasticity, linear viscoelasticity effect, because there is not much rate effect on the Young's modulus.
And can you comment on how you compare to models like Professor Nguyen model?
I don't know I've been working with Nguyen, but it's not the same. So I would be very pleased to have a look at that. And if you can by email send me, and I'll be pleased to talk with you more. And I know your work, by the way. I certainly recognize your name. But I'd be pleased to have a look and see how it compares.
Okay, thanks a lot.
Thanks a lot to you.
Okay, Filippo Agnelli.
Yes, thank you, Manas. Good afternoon. I am Filippo Agnelli. I am a PhD at LMS, École Polytechnique. I've got this question since the beginning of your seminar. How can you afford to have such a big and complex model within finite element computation? You've answered a little bit these questions at the end, saying
Yes.
that you could only simulate structures of roughly micrometer size. But
Yes.
This is applied to composites, and I assume it's interesting to also model the both fibers and matrix. How can you how can you combine these? Can you give us some insight on this with this regard?
Yes, and I would say even more. This is 2D, huh? So we're working on a 3D version of the code, and then it will be even more complicated to do something realistic at scales beyond a few micrometers. So I certainly agree with you. So basically, this is the scale of a model that we can treat with finite elements. So 3 fibers. But what I said at the end is that you can use this model for 2 things. Understand better what's going on at that length scale, over time scale that are long, much longer and length than MD simulations. You can look at the mechanics here. You can do nano indentation, things like that, very carefully. Understand what are the possible size effects, for instance. Do compare to micromechanical test. We have made comparison with DIC measurements during this in situ compression test, but nothing more. I agree with you. So basically, you can use such a low scale model perhaps to fine tune another constitutive model, which would be a classical constitutive model to make prediction at a higher length scale. So my point is absolutely not to say that this is the model and now you can forget the rest. This is complementary. It's like people working on strain gradient plasticity. Even though you can deal with bigger problems with strain gradient plasticity, the computational impact is huge, and so it limits also the size of the models you can predict in 3D. it's a bit the same story. So it would be inside a chain of models that we need. For an homogeneous material, a bulk polymer, well, there you can assume that if your domain size is big enough, you can properly capture a compression test, a tensile test, etc. But for a composite, you're right. Yeah. No, you're right.
Okay. Do we have other questions? Yes, we have a question from Paras Kumar. Please go ahead.
Hi, thank you. Thank you, Professor, for the nice talk. I'm Paras Kumar, a PhD student working on modeling fracture in polymer nanocomposites. So I have two questions. First one is like, so in all your presentation, you were focusing more on compression rather than tension. But what I've seen mainly is, yeah, tension test is usually done. So is there a particular reason like compression gives more knowledge to us about the material's behavior or something?
Yes, in the present system, so the RTM6 system, it fails in tension after about 5% deformation. So if we want to have access, macroscopically 5%. Of course, this has to do with the defect I mentioned at the end, but in smaller volumes, the deformation you can reach before damage is much bigger, because for instance, what you see here, you see some damage in the composite, but this is after 30-40% deformation. And so even some region might be in tension and not fail yet, because you don't see starting defects, or you will get the cohesion probably before. But so if you want to get some knowledge about the large strain viscoelastic, viscoplastic response, compression is better suited. And that's true for many high-strength polymer systems. Not so many are ductile in tension. So compression is needed, and you have to be very careful with compression because of the friction. So we use lubricant, Teflon, or different method, and also DIC to correct for the barreling effect. But we do a lot of compression indeed. We do a lot more of compression nowadays. And you had a second question. I don't remember.
Yeah. And the second one was like, so in order to model size effects, and so I mainly work with particle composites. So you have like spherical particles in a unit cell. So and there, in order to model these size effects, you need to somehow take into account like what happens in the interface region around the filler particle. So yeah, like this chemical measurements show that the interface region is somehow different from the matrix. So are you also here, like, I would like to know, like, is there any model where you're trying to model this thing?
It's an excellent question, and we are really interested by looking at this. We have not yet addressed this point, and you're right. In this 1 or 2 micrometers channel between the two fibers, we certainly know that the sizing that is put on the fibers reacting with the matrix to get good adhesion is affecting the chemistry and the molecular structure over a size, and AFM measurements have shown that it's over a length scale which is on the order of hundreds of nanometers, something like that. So there is certainly a transition zone here, which is an interface region where the properties should be different than the properties, also perhaps the chain alignment, something. So there is certainly something there, and something on the other side, which is a decent fraction of the volume that has a different properties, and we are thinking about trying to address that with the STZ model to see what we can do. But we need more experiments to find out what is the physics, the nature of the structure here nearby, before introducing something into the model. But that's a very interesting point. And I think up to now, what people do is most of, I think, people, they put cohesive zone model to simulate the cohesion process. And by fitting the right peak stress and energy in the cohesive zone, somehow they take into account this complexity of this interface layer, and they just merge everything in a black box. And it's better to do that than nothing, of course. But there is probably a lot of interesting physics to scrutinize at that length scales, and I understand that's what you do, and that's very interesting.
Okay, we have time for one last question.
Thank you very much for your reply.
There is one last question. Okay, so thank you again, Thomas. Thank you very much for taking this time, and wish your grandmother a 100-year,
Yeah,
very nice 100-year anniversary.
Thanks a lot.